Our approach to this problem is that if you want to use electricity to rearrange bonds and do chemistry or store that energy, the rubber meets the road right at an interface. What we mean by an interface is it's the boundary between a solid and a liquid. And you need a boundary between a solid and a liquid because the liquid is usually where the ions and the molecules that you want to do the reaction on exist. And the solid, usually a conductive solid, is where you bring in the electrical current. So anytime you want to use electricity to rearrange bonds, you need an interface. And so our entire group is really focused and dedicated to understanding how to manipulate those interfaces and engineer them really at the atomistic and molecular level. And our approach to this problem is very much rooted in not sort of trial and error. We don't try a material, figure out whether it's good, and then sort of pick another material to try again. So what we really try to do is take a material that we understand something about, try to understand the individual steps that molecules take when they rearrange from one unit to another at that surface. And once we understand the mechanism, the sequence of those individual steps, we then hone in on the factors that relate to that surface chemistry that we can manipulate in a systematic way to be able to change those processes. And what this really allows us to do is go from the sort of trial and error statistical probability of are we going to make a new material, are we going to be able to tackle this problem, to much more of a directed approach that is focused on the very fundamentals of how each step occurs. And the power of this is that you not only learn where to go to make new materials and make new interfaces, you also learn very quickly what individual steps in the overall process are really challenging and which are easy. So you can direct your efforts in a much more targeted fashion. And so we're very much driven by understanding what we call mechanism, the steps by which reactions at surfaces occur. And our sort of forte is really in understanding those using a range of different tools brought to the problem, tools that involve the use of light to shine on that surface to be able to understand processes that occur at an atomistic level. We use a lot of tools that allow us to build those surfaces from the bottom up at a molecular level. And the combination of those two really allow us to get an atomistic picture of every single elementary step that occurs in the reaction. And we can use that to design new materials with a much greater degree of fidelity than one would ever be able to achieve by sort of trial and error approaches. So everything we've discussed kind of so far is very much in the abstract of like how do you control what's happening at an interface at a molecular level. But maybe I can pull back a little bit and say some of the things that we're really excited about in terms of where this can lead and where this can have a transformative impact, especially in the energy space. So one area that we've gotten really excited about recently is in the enormous environmental problem and enormous energy transition problem around how you better utilize methane. Methane is a lower carbon resource than, for example, coal, but it's remarkably underutilized because oftentimes methane is found in remote areas that makes it hard for it to be transported to market. So one of the chemistries we developed over the last few years is one that allows us to use a well-defined molecular unit and the input of renewable electricity to convert methane into a much more easily transported liquid fuel like methanol. And the fundamental chemistry that we've developed allows us to now think about taking stranded reserves of methane and converting them into a liquid fuel and important chemical intermediate that can be much more easily distributed and much more easily utilized ultimately. And so we're excited about this as a prospect not only for reducing the enormous problem of methane flaring. An interesting statistic is that the world just burns, flares essentially, methane at a rate that's so high that the amount of global flaring of methane is equal to almost 25% of the amount of methane that the U.S. natural gas that the U.S. consumes each year. So the globe burns with no economic or energy output an equivalent amount of methane to 1/4 of U.S. demand in a given year. So the challenge is enormous, and the perspective we bring to it is that it really lives at a nexus where new approaches that deploy and utilize renewable energy could be very, very powerful for addressing this problem. That's one area that we're very, very excited about.
Another area, of course, there's the environmental issue. You don't want all that methane being burned. You're concerned about the atmosphere.
That's correct, right? So the tragedy of methane flaring is that it's purely related to the challenge associated with storing it and transporting it. We have ample need to use that methane. We have ample need to use derivatives of that methane to make everything from pharmaceuticals to plastics. And yet an enormous amount of it is simply burned because we don't have an easy way to transport it. So this is an area where innovation can really address what is a long-standing and actually growing environmental problem. As we start to transition to some of these lower carbon fuels to a greater extent, we'll be facing this with even greater urgency in the future.
Well, I know these are early days, but how do you think some developments like this would eventually turn into commercial reality?
What we would be really excited to see projecting out in the 5, 10, 15-year time horizon is the ability to take the fundamental chemistry we're developing, say in the context of methane conversion, and be able to make from that portable devices that could actually be used out in the field at remote methane sites that would allow you to then use renewable electricity to actually be able to convert that methane into an easily transportable liquid fuel. That would be a true game changer in the context of a methane economy or a methane economy that we use as we transition to renewables. And we don't have the technology right now to do that. In part, we don't have that technology because we don't have the basic science that underlies that technology. One of the points I always like to stress, especially with companies that are interested in investing in MIT, is that the real value-added proposition we offer is that I view MIT as a knowledge house. And what that really means is that we can provide the insight that will ultimately form the basis of all of the emerging future technologies that are going to define a new landscape in energy. And so our group very much is focused on the fundamental science, and the value of being at MIT is that we have an enormous ecosystem to then take that further, ultimately to deployment, to device scale, to actually into the marketplace. But investing in MIT oftentimes really requires having a time horizon that's well matched to the nature of the problem. Right? So for us, we don't want to necessarily tackle and make incremental advances to those technologies that are already in the marketplace. We think that oftentimes industry is already well suited at making some of those incremental advances. What we'd like to do is develop the basic science that would underlie the sort of paradigm shifting or disruptive technologies that might be there 5 or 10 or 15 or 20 years from now.